Okay, so I'll try to spend actually one academic hour, say 45 minutes, talking about basics of astronomy. And at first I'll start with 10 facts about astronomy as science. Fact number one: astronomy is an observational science. So this is something peculiar, I'd say, because normally natural sciences, they are experimental scientists. So you take an object and you make experiments. So if you take, I don't know, a smartphone and you want to make experiments, at first you want to break it probably, or at least to open to see what's inside. We cannot do it with stars. So we can only observe what's going on in the universe, and it makes astronomy special. So methods are really different, and people spend much more time on data reduction and numerical modeling, so I'll talk about it later. But we start with the fact that astronomy is the science of observers. Okay, when typically somebody hears about astronomical observations, immediately they imagine a person staring in a telescope. Of course, people do not do it for, well, I would say for centuries, at least for more than a century. Definitely you can find a person who's staring at a telescope, even if it is a big telescope. But then this person is a technician. So still there are some operations which are necessary to prepare a telescope to perform in an observational mode, which can require some human appearance at the telescope. But of course, as soon as it was possible to fix an image, at first of course to make a photo and then to make a digital image, people immediately started to do it, because then you can apply different sophisticated methods to study the image, and it's much better than you have just a momentary impression of what you see. But still, like if I'm not mistaken, 70 or maybe 80 years ago, at least in the Moscow State University, it was impossible to start studying astronomy if you have well, not ideal eyes, I would say. So if you have glasses like plus minus 10, 80 years ago it was impossible even to start studying astronomy, which is of course peculiar. So we have observations, we obtain images, and then people use different sophisticated methods for data reduction. Typically, when you see a professional astronomical image, it is a result of very sophisticated procedure. So let's have a look at these two images. We'll start from the right one. This is a unique exoplanet system, HR 899, and this is a unique case in which we see 4 planets in one system. Definitely it is impossible to see by an eye, even if you look at the largest telescope on Earth, or if you fly to space and use some space telescope. This is a result of a very sophisticated procedure. You have to, at first you have to use some special equipment to reduce the contribution from the stellar light, and only then you can see these 4 dots, which are 4 planets. As a rule, planets are started to be numbered by the letter B, so B, C, D, E. A is the star itself. And to obtain such an image, you really have to put hands on the data. It is impossible just to make a photo, to point a telescope to a particular patch of the sky, press a button and obtain an image. It doesn't work like that. What we see on the left image, this is a supernova remnant. So centuries ago, a star exploded, and now we see a nebula which is expanding. It was really an explosion. Can we see something like that with the naked eye? The answer is definitely no, because this is a composite image. made by putting together an optical image, an X-ray image, and an infrared image. And colors are artificial here because, of course, we just don't see anything in X-rays or infrared. And it happens very often that you see some nice colored image, but colors are fake simply because people are observing in some energy range which is invisible by human eyes. But of course, on this image on the left, any tiny filament is real, and we can measure its velocity. Very often we can measure its composition and so on, but the image itself is in a sense artificial. It's like you make your photo, your X-ray completely of your body, your MRT, and put it all together with some artificial colors which allows you to distinguish between different images. And so it's often the same, a similar approach is used in astronomical data. Okay, already I mentioned observations in X-rays and infrared. Indeed, now astronomers use the whole electromagnetic spectrum for observations. So on the left we see a radio telescope, in the middle an X-ray telescope in orbit, and on the right we see a ground-based gamma ray telescope. This is a peculiar thing. Unfortunately, I have no time to speak about this technique in length. In addition to electromagnetic observations, people use observations of everything coming from space actually now. We have neutrinos coming from stellar sources, so there are neutrino detectors for astronomy. There are different particles which are jointly called cosmic rays, so there are different detectors in space and on Earth to detect these particles or products of their interaction with the atmosphere. And the last window to the universe was opened nearly 8 years ago, in 2015, when for the first time we started to observe directly gravitational waves. So these are all guaranteed types of observations in astronomy, and astronomers are actively using all of them together. And of course, each type of observation brings new type of information, so it's very important really to do it together. And definitely it doesn't work like that. Now we have X-ray telescopes, so we do not need radio telescopes, for example. No, we need all of them because they bring different information. Again, you can think about just about images of a human body, of X-rays, MRT, and so on. There are different kinds of telescopes, and when somebody tells you that he's an astronomer and he's an observer, immediately you think that the guy is spending much time at different interesting sites where the telescopes are situated. It's not necessary so, because typically radio, well, not only radio, that's just the best example. Different telescopes can be operated remotely, and of course there are no astronauts near space-based telescopes, and typically if there is a team of people working with a telescope on the ground, most of them are engineers, technicians, and so on. So very often really an astronomer even doesn't need to go on the site. However, sometimes it happens, and sometimes it helps to do something better, but again, not necessarily. On the left you see an operating room of one of large telescopes, and definitely I'm sure that if you immediately make people in the room falling asleep, then take them all and move them to a copy of the same room tens of kilometers from the telescope, they will just continue to operate the telescope with the computers, and that's it. And even amateur astronomers very often are not sitting near their telescopes. On the right you see actually quite old small telescope. You can guess that it's quite old looking at the laptop, of course. And very often, especially if it is, I don't know, winter, -20 outside, then just the telescope is outside and astronomers are sitting in a warm room at the computer, because anyway they want to have nice photos, for example, to put them in Facebook. Okay. Astronomy mainly now is a part of physics. Not completely, and I'll talk about it a little bit later, but the main modern part of astronomy is astrophysics, and in this science we are interested in the nature of the sources of objects which we are observing. And so we ask different questions, not when and where, but how. And so astronomy is part of physics, and typically, again, if you take an average astronomer just picking it up in the street, then most probably the person got his first degree in physics. There are exceptions, but they are really exceptions, maybe a few percent, 10% in total. Astronomers actively use supercomputers simply because we cannot do normal experiments. The same thing, by the way, is with, I don't know, nuclear weapons. You cannot make nuclear tests, luckily, and so people simulate. In English, there is a nice expression that those who can do it, those who cannot do simulate. So astrophysicists simulate different processes, and very often, of course, you need huge computer resources, so using at least clusters is very typical. But sometimes people use real supercomputers, not just 64 processors or something like that. Okay, so it is even working. This computer simulation of coalescence of two neutron stars. Maybe this is also working, I don't know. Yeah, and this is a simulation of a large-scale structure formation. So here we see evolution of a cube of a cosmological size of hundreds of millions of light years across. Okay, back to observations. It is possible to say that mostly the main results are obtained with large and expensive instruments. The reason is quite simple. Those important results which could be obtained with smaller and less expensive instruments have been already obtained. So that's it. And continuously we need new telescopes, more powerful, with better parameters, and unfortunately they can be really expensive. So on the right you see one of the, at the time of construction, it was the most expensive camera in the world. That's the Wide Field Camera 3 on board of the Hubble Space Telescope. So it costed more than $100 million. On the left you see a telescope, so without equipment, without any instruments. It costs about $1 billion, and that's the scale of large telescopes today. Still we can build new telescopes relatively rapidly. For example, recently we were discussing at the lunch with colleagues. I'm working in a theoretical physics institute now. So people came from a conference about particle physics. So there was a session on accelerators, and colleagues called it depressing, because the timescale of construction tell us that the next big accelerator, something which comes after the Large Hadronic Collider, will be built, say, in 2070. So I guess that most people at the table during the lunch, they will be dead at that time, and it's a little bit depressing indeed. In astronomy, things still happen a little bit faster, and this continuous technical progress results in huge flow of data. And this is very nice, and the modern tendency is to make this data open. So data, not often immediately, but say after 1 year, is available to everybody. And that's very nice because you can cross-check, you can derive additional information from the same data, because very often you have, for example, many objects at an image. But you as an observer are interested particularly in one source, but other colleagues can be interested in other sources in the same image, so they can use it. Or even about the same source, they can ask different questions. So it's really a great advantage that nowadays data is in open access typically. So this nice picture results in a huge flow of results. So now about 2,000 original papers are published monthly. This is really a lot, and of course it's impossible to follow, even to follow all the news. So not going into details, but at most what you can do, you can read all titles of papers, but typically people do not do even this, so they follow papers in their field, and sometimes it's a relatively narrow field for many colleagues. So we are living in a time of really huge flow of new scientific information, and it's interesting, it's fascinating, but on the other hand it brings some difficulties. Okay, so I hope now you believe me that astronomy is a modern, rapidly developing science. Mostly it's a part of physics. It performs very interesting observations. They are reduced in a very sophisticated way. To understand better nature of different sources, we use advanced theoretical approaches and use advanced numerical modeling. And now just a few words about different parts of astronomy. This division can be done in several ways, so I prefer this one. So it's very nice to divide many things in 3 parts. So astronomy in this approach consists of 3 parts: astrometry, celestial mechanics, and astrophysics. So astrometry is the oldest part of astronomy. So initially astronomy was a very applied science. So it appeared not because people were fascinated by the sky, but simply because they needed a calendar and they needed to navigate. So astronomy really answers questions where and when. And that was again the first part of astronomy. For many people a relatively dull thing, very applied and very mathematical, I would say. But new results brings new approaches even in this oldest part of astronomy. For example, we can use now radio pulsars for navigation. And modern satellites start really to do it. And this is a very interesting thing, so it completely reshaped the idea of space navigation. Using pulsars, a satellite can navigate completely independently from connection to the Earth. The other interesting thing is the appearance of astrometric satellites, which can perform very rapid and very precise measurements of stellar properties, and not only stellar, much better than it's possible to do from the Earth, from the ground, because the atmosphere doesn't prevent high precision of these observations. Okay, celestial mechanics. It appeared more or less since Newton formulated his theory of gravity, and so it became possible to calculate, in a sense, to predict how the celestial bodies will move. And it was very interesting and important, and it really was part of mathematics, I would say. And say in 18th, early 19th century, that was the best time for this science. But as time goes on, new things appear, and now we have a new theory of gravity. We have general relativity. Also, we have special relativity, so they are used for precise calculations in celestial mechanics. And it's very interesting. Then there are very interesting results related to chaotic dynamics. And finally, the third part, astrophysics. As I said already, now this is the largest part of astronomy. So really, say 3 centuries ago, an average astronomer would do astrometry. 2 centuries ago, most probably celestial mechanics or something related to it. And now an average astronomer is doing astrophysics. So that this is really part of physics. It is rapidly developing now, and it is rapidly developing because we have new instruments, and this makes life of an astronomer very fascinating now. So a few words more about each part. Astrometry, they always used sophisticated observational devices. So on the left you see a very ancient device, but for this time it was very sophisticated, very expensive by the way, and very precise. So that was the best that people could do at that time. On the right you see 2 astrometrical satellites, Hipparcos, which was in orbit 20 years ago, and Gaia, which is in orbit now, and it is producing really wonderful results. And here we are. That's the first Gaia release. That's the map. Any tiny white dot in this plot is a star, and on the whole there are about 1 billion stars in the catalog of Gaia. And it is possible to measure their position, how it is changing with time, to measure velocities, to measure spectral properties of stars, and it allows us finally to make a 3D map of the galaxy. And this is important for really all parts of astronomy. And Gaia is a very successful project. It produces a huge flow of data, and there are many releases, and even when the satellite will stop operating for several years, people will continue to reduce the data to obtain new information out of it. For example, it is expected that Gaia alone will find about 10,000 exoplanets, so planets around other stars. Celestial mechanics, in brief, it's calculating of orbits, but this can be a very difficult task. And say before computers in 19th century, teams of astronomers could compete in rapid calculation of a freshly discovered asteroid orbits, for example. And people really went mad. I mean, so they really finished in asylum after this huge intellectual effort. So you have to be careful, because I suspect that it's possible with computers anyway. So if you code too much. In celestial mechanics there are interesting problems even now, and the best known, just recently, yesterday, there was a new paper about it. People presented new numerical, by the way, calculations. That's a problem of another planet in the solar system. So sometimes it's called planet X. So it's not planet 10, it's not Roman 10, it's X. Absolutely unrelated to the former Twitter, by the way. Okay, so the problem, as you probably heard, is like this. There are many small bodies with sizes about 100 kilometers, say, across beyond the orbit of Neptune, and it became clear some time ago that these orbits are not randomly oriented. So that they have some preferences, so it looks like a kind of a butterfly, I would say, and it is necessary to explain why they have such a configuration. And one of the ideas is that there is a massive body, another planet, and the gravitational influence of this additional body shapes the configuration of orbits of these trans-Neptunian small bodies. So people are looking for this planet. It's very difficult to find it because it's very dim, because it's far away. It doesn't have its own sources of energy, so it just reflects the solar light, and being very far away, it might be a very dim object. In addition, it can be out of the plane of the solar system, so you have to look at a huge patch of the sky. And unfortunately, it is, well, maybe not impossible, I would not say impossible, but extremely difficult, and people did not succeed up to now to calculate with reasonable precision a possible present-day position of this planet. So people really have to look nearly in the whole sky for this planet. Maybe next year a new huge telescope for surveys will start to operate in the south hemisphere, and maybe it finally will allow us to find the ninth planet, or to close the question. Then, of course, theoreticians have to use other hypotheses to explain properties of these small bodies. So indeed, celestial mechanics, which for many people seems to be a relatively dull science, sometimes it brings new, very fascinating problems. Okay, and astrophysics. As I said, now quite typically astrophysics is really synonymous of astronomy. So we are dealing with studies of nature of celestial bodies. And in the rest, I don't have much time, by the way, but still, in the rest I'll present 10 main facts, and they are facts from astrophysics. Okay, here's the list, so I'll go one by one relatively quickly, and let's go. 10 facts is maybe not enough, but still with 10 elements you can guess the shape of an object. So I think that 10 can be enough for our purposes. Okay, so the first fact is that our sun is a star. There are many stars in our galaxy, about 300-400 billions, and stars are objects in which thermonuclear reactions are going on. So the most typical reaction makes helium out of hydrogen. There are lots of stars in the galaxy, but the galaxy is huge, so typical distances between stars are much larger than their sizes. Typical distances between stars are about few light years. That's why it's very difficult to travel between stars. So, for example, if you can travel in a planetary system around the star, to jump to another star, that's really a huge jump. It's very difficult to do it. But if you can travel in a galaxy, then the jump to nearby galaxies is not that big, I would say. Our sun is a star, and it has its solar system, and very often people incorrectly understand where the solar system is ended. Some people really think that the orbit of the last planet is the limit. It is not so. Then very often you can read that Voyagers, these interplanetary satellites, left the solar system. Again, it is incorrect. So the basic definition of the solar system involves gravity. So we have a solar system while the sun gravitationally controls movement of different bodies. And so roughly we can say that the boundary of the solar system is in the middle between the sun and the nearby stars. As you already know, typical distances between stars are about few light years. So the size of the solar system roughly is about 1 light year, which is a huge distance. From Earth to the Sun, you know, is roughly 8 solar minutes. So 1 year is definitely much longer than 8 minutes. So the solar system is big, and the boundary of the solar system is in some sense formed by comet nuclei, by small ice bodies with a typical size about few kilometers. And on the left you see a 3D map of the solar vicinity with different nearby stars. So each star has its own system around it, and the scale of this image is about a few tens of light years. Okay, the next fact. Stars are continuously dying, and new generation of stars appear. So let me show the second image. Stars continuously are formed from the interstellar medium, and when a star dies, it expels its outer layers back to the interstellar medium. As during a stellar life new elements are formed inside the star, these outer layers, which are expelled in the outer space, they have different chemical composition in comparison with the original nebula from which the star has been formed. So this process results in a chemical evolution of the interstellar medium, and new generation of stars are formed from this interstellar medium, so we can talk about chemical evolution of the galaxy. Of course, it goes in one direction. You have less and less light elements, and you have more and more heavy elements. Stars are very different, and so their evolution can proceed in a very different manner. A little bit surprisingly, I'd say, massive stars have short lifetimes, and the smallest stars live long, and at a limit they live infinitely long, I would say. The most massive stars, they live just for a few million years, and typically they explode at the end of their life, forming a neutron star. Some of them can form black holes. It can happen even without an explosion. And light stars can live for billions of years. This is so because the intensity of thermonuclear reactions inside a star depends on the temperature, and temperature depends on the mass of the star, because massive stars say press on the matter in their nuclei stronger, and so temperature is higher there, and reactions go very rapidly. And even having a larger amount of hydrogen available for reactions, a star consumes this amount of hydrogen much faster. So at the end, as I said, massive stars produce neutron stars or black holes sometimes. Less massive stars, for example, stars like our Sun, at the end they produce white dwarfs, A white dwarf is a very interesting object. It was actually the first microscopic object for which quantum mechanics was necessary to explain its properties, to explain its stability. So it was understood even slightly less than a century ago. It was in end of 20s last century. A typical white dwarf has a mass about half of the solar mass, and the size about the size of the Earth. We observe stars at different stages of their evolution. We observe different stages of stellar formation, starting from protostellar nebula and up to formation of stars and planetary systems around them. So on the right you see a composite image. In the center you see a star. Okay, the stellar light is reduced at the image, otherwise it would be too bright. So there is a star in the center, there is a planet around it, so this white dot is a planet, and we see it not because it is reflecting the stellar light, but it shines by itself because it's young and it is still contracting, so it has its own source of energy. And we still see the material around the star in the form of a disk, as we see it in the projection. So we see the disk nearly age on, and it looks like two jets, but they are not jets. There is just a disk around. So this is a fresh star, a star which was born not so long ago. We see different stages of the final episodes of the stellar life, and we, in several cases, there are really very few, there are like several tens maybe, up to now, we know which star exploded in a supernova. So the history in all cases is like that. You observe a supernova, then you look if there are archival photos of this region of the sky, and then few years after the supernova again you obtain an image of the same region, and you start to count stars. So this is a small piece of a faraway galaxy, and we see that this star, this orange giant visible in the left plot, is missing on the right. So we know that this star really exploded. So in principle we have information about the whole life cycle of stars of different masses. Okay, we talked about stars, now about galaxies. We live in a galaxy. It was also understood not long ago, a century ago. So, for example, in the beginning of the 20th century, nobody was sure that galaxies really exist. So I don't know whom to mention, but Gauss didn't know that we live in a galaxy, for example. So galaxy is a huge system. Our galaxy has a typical size about 100,000 light years, and when we look at images we would say that galaxies consist of stars. Also there are dust and gas inside them, especially in spiral galaxies similar to our galaxy. And as I told you, galaxies are relatively well packed. So the nearest galaxy comparable to the Milky Way, the Andromeda galaxy, also known as M31, is just 2.5 million light years away. So our galaxy is 100,000 light years across, and here it's just 2.5 million light years away. If you compare between, say, an astronomical unit, which is the distance from Earth to the Sun, and typical distances between stars, then in the later case the jump is much larger. Galaxies can have different shapes, so basically they can be disks with spirals. There can be elliptical galaxies without interesting structures. There can be irregular galaxies. And there can be interacting galaxies. So as galaxies can come close to each other because of gravity, they start to interact with each other, and then really funny shapes can be formed. Okay, now we make a jump not in space but in time. The next episode is about exoplanets. You already saw the picture on the right. This famous system with 4 visible exoplanets. We know systems with 5, 6, 7 exoplanets, but they are observed indirectly, so we do not have images. Here we really have an image. On the left you see a planet. Actually, you already saw it before. Let me maybe jump back to remind you. Here it is, this one. Now we zoom a little bit. And these 2 images are obtained with a time difference of several years. And you see that the planet made the half of its turn around the star. Altogether, we know more than 5,000 exoplanets up to now, and there are many candidates, and the number is increasing. But of course, the idea is not to find just many exoplanets, but to understand better their properties, their nature, their origin, their evolution. And to do it, inevitably, we need to discover more planets just to discover more interesting, peculiar cases. Okay, my time is running out, and now I came to the last part of the last part. It is related to cosmology. So I'm trying to be fast here, but I hope that you'll ask me questions about this part. So the basic fact about cosmology is that the world as we know it, I underline it, not the universe in some very general sense, but the world as we know it has a finite age. It means that even if you take something which is eternal, like an electron, it cannot decay to other particles. Yeah, it is absolutely stable. It can disappear in an interaction, but by itself it's stable. So even the oldest electron in our world has a finite age, and this age is slightly less than 14 billion years. Yeah, sorry for the thunder. We will really have a storm here now. So our universe has a finite age, and this is the basic fact. The universe is expanding, it is evolving, so it is changing. Say, even a century ago, it was nearly unacceptable for many people, including Albert Einstein. In relation to this fact that the universe has a finite age, there is an interesting paradox called Olber's paradox, and in Russian I suggest that people read this book. Otherwise, if you are interested in a very simple question, why the sky is dark, you can simply go to Wikipedia and read about it. Okay, the universe is evolving, we can model it, and there are many interesting numerical simulations related to this subject. And we really observe different stages of the evolution of the universe, simply because the velocity of light is also finite. So when we look at distant objects, we observe them in their past. For example, we know that galaxies form galaxy clusters around us. But in the beginning, there were galaxies, but there were no galaxy clusters. And we can observe this epoch. It is the first billion years of the existence of our universe. And on the right, you see zoomed square from the left image. And these 6 red objects, they are 6 faraway galaxies. Now they form a cluster somewhere, but we do not see them now. We see them in their youth, and at that time they did not form a galaxy cluster yet. So this feature that the velocity of light is finite, this allows us to really observe the history of the universe. And because the velocity of light is finite, we cannot say everything. So we just observe a sphere around us. There is a cosmological horizon. So there are much more galaxies behind this horizon, but the light from these galaxies simply did not reach us yet. So we can observe this galaxy, but galaxies behind our horizon, they are invisible for us. The universe by itself is evolving, and also we can talk about the chemical evolution of the galaxy, of the universe. So not only of the chemical evolution of the galaxy, but also about the chemical evolution of the universe, because in the very beginning the universe was very simple and actually no chemical elements existed. Then hydrogen appeared. In early universe only helium was formed in a significant amount. All other elements, they were formed afterwards, most of them in stars or in different processes related to stars. And as we already said, there is such a circle, a cycle in the interstellar medium, and on each cycle we have more and more heavy elements, and that's important because we are made of heavy elements. We are not mainly made of hydrogen and helium, and this means, for example, that the first stars, they could not have planets similar to the Earth, and so it was necessary to wait for some time till life became possible in the history of the universe. So no living creatures could appear, say, in the first 1-200 million years of the universe at least. And so I'm rushing towards the last fact about the composition of the universe. As you know, it's quite peculiar. The universe consists mainly of God knows what. So there is normal matter, we call it baryonic matter, because it's made of protons and neutrons, so chemical elements. But this normal matter, this baryonic matter, contributes just 5% to the total density of the universe. All the rest is dark energy and dark matter, and both of them still are in the status of hypothesis. So we do not detect directly dark matter or dark energy. We have some sets, that's important, not a single observation, but sets of different observations. There are different theoretical considerations behind it, which is very important. And the best explanation for what we observe can be formulated like this. The universe is mainly made by dark energy and dark matter. Dark matter has been proposed long ago, already in 30s, so nearly 190 years ago, if you like. It was made by Fritz Zwicky, who studied galaxy clusters, and he demonstrated that inside galaxy clusters there is some additional mass formed by something invisible for us. At that time he didn't make any hypothesis about exotic particles or tiny black holes or something like that, but that was a clear fact that there is an additional mass inside a galaxy cluster. After 90 years we are even more sure that it is necessary to add some additional mass to galaxy clusters. There are some interesting individual results, maybe I'll skip it, but as astronomy is an observational science, we are looking for some peculiar examples, for some peculiar processes in the universe, and it seems that the universe can separate normal matter from the dark matter if two galaxy clusters collide. And there are several examples of such colliding clusters. That's the first and the best known, so-called the bullet cluster. And it gives additional evidence in favor of the dark matter. Okay, so maybe I'll skip some observational data. We're looking for dark matter. Of course, the best way to detect it is to find it in Earth laboratories. But as soon as it's not done yet, astronomers look for astronomical indications of the existence of the dark matter. And in many theoretical models, dark matter particles can annihilate when they interact with each other, and this might produce additional radiation, typically gamma ray emission, and people are looking for such additional emission. Also, there are different pieces of evidence in favor of dark energy. So dark energy is a joint notation for different models which explain accelerating of the universe. So if you think about an expanding universe, then of course you can guess that gravity works against this expansion. So the natural expectation is that the universe is expanding slower and slower because of the gravity. However, observations at the very end of the last century, of the last millennium, if you like, demonstrated that indeed the first 5, 6, 7 billion years the universe was expanding slower and slower, but then something happened and the universe started to expand faster and faster, and now we are living in an accelerating universe which expands faster and faster. We do not know exactly the reason, but the best set of models is related to some additional ingredient of the universe, which is called dark energy, which is responsible for this accelerating expansion. And now there are many very different observations related to observations of supernova, of the cosmic microwave background, of large-scale structure, which all together point towards the existence of this additional ingredient in the universe, but still the nature of the dark energy is not known. The nature of the dark energy might define the future of the universe. So it is very difficult, I would say it is impossible for us to make a definite prediction about the future of the universe, if it is going to expand forever or it is going to recollapse after some time, after some billions of years, without precise knowledge of properties of the dark energy. But anyway, the universe is relatively old, it is evolving relatively slowly, so for the next tens of billion years, most probably it will continue to evolve in the manner in which it is evolving now. Okay, so that's it. I'm still all right with making it in less than 1 hour. So now we can come to questions, and you can ask them now, and in principle you can also find me in Telegram, and there is a chat for asking questions. So sometimes I make streams answering these questions. Those who read in Russian can follow my project with regular news, and also those who read in Russian can find my book, which is about the universe, but definitely you cannot read it in 1 hour.